Hi class, welcome to lecture 25 of AREC 333. Today we will continue with linear program, and we will continue with the farm management example that we set up last time. And since we already set up the problem, the focus of today's lecture is going to be how you interpret the results that you can get from solving that linear programming problem. And we will spend a little bit time on the answer report, and then we will be mainly focusing on the sensitivity reports. And before that, I will introduce to you guys what is sensitivity analysis. I'm not sure if you have heard of this word from other occasions, but we will do that for this course. And also I want to mention is that I showed you guys one way of setting setting up the linear programming problem for this example. There's actually another way, which having less constraints and less decision variables. So I will briefly go over the alternative setting of this problem as well. And there's in the Excel solver template I provided, there's actually a setup for both settings. So if you're interested in the alternative setting, you can spend a little bit time there. So the readings are really the same for last lecture, and I will not spend time here, but I do want to mention that there is an example in deburring that is very similar to this example that I'm using. So if you're interested in one more example, you're welcome to study that example in deburring as well. So first is this is the setup of the problem that we had from last lecture, and I actually want to spend a little bit more time on the last three constraints. I thought those three constraints are not straightforward, and there might be difficulties understanding those constraints based on the experience from teaching these last year. So let me spend a little bit time here. So the first one, there's actually something in common for all three constraints here, is that for each product, there's actually a relationship here, is that the quantities sold and the quantities used for both corn, soybean, and cattle. So quantities sold and quantities used should be smaller than the quantities yield by production and the quantities bought. So this is similar for all three of them, although for some of them there's no bought, or for some of them there's no used. So basically it's having the same relationship here. So let's look at cattle here first. For cattle, it's easy. There's quantities sold, there's no quantities used. So all of the beef produced are sold. There's no consumption by the producer or any other use of it. So quantities used is 0. And then the quantities yield by production is yield by raising cattle. So that's the quantities yielded by production. And again, for the cattle product, there's no quantities bought. So this is also 0. So it ended up with beef sold smaller than the quantities yield by production, and the production is with cattle. So here, the relationship here, the coefficients are both 1. This actually depends on the units here, is because if you go back to your to the budget, which was given in the verbal problem, if you go back to the budget, you will find that one head of cattle is able to produce pound of beef. So that's why here the coefficients are both 1. So this one should be relatively easier to understand. However, for the corn and soybean, it will be a little bit more complicated. So let's focus on soybean. For soybean, it's similar to cattle in the way that there's no quantities used, there's no quantities bought. However, here yield soybean is a little bit more complicated. It's because this is your decision variable, the acres of land that you use to raise soybean. So this is your decision variable. And if you want to link this to the quantities yield by production, you actually have to times the yield. So the yield information you can get from the budget, from the table. There, it actually have the yield, which is there's 30 bushels per acre. So that's why in this soybean constraints, you have to times 30 by the decision variables. And together, the product of those two terms is the quantities yield by the production. And on the left-hand side is the quantities sold. So if we go back here, you will find there's a minus 30 here. And for the other one, they sell beans here. It is 1. So go back here, it's because, so here is 1 times the quantities sold, and this site is 30 times the quantities, the acres used to raise soybean. And if you move this whole term to the left-hand side, right now it's on the right-hand side, to the left-hand side, then you add a negative sign in front of this 30. So it becomes negative. That's why we come up with this negative 30 here. It's because we're moving it from the right-hand side to the left-hand side. So that's how we got this soybean constraint. And for the corn constraint is a little bit more complicated. So for corn, we have both sell and the quantities used. So the quantities used here is we have to times by 25. This is because for the cattle feed, for 1 cattle, we need 25 bushels. So the unit is 25 bushels per head. So here you actually times this 25 bushels per head times the heads of cattle. So that's, and then the product of those two are the quantities of corn for cattle feed. And on the right-hand side, this is the quantity yielded by production. So again, we have to times 125, and this one is actually the acres of land used to raise corn. And for corn, we do allow to buy corn from the market. That's the other variable there. And again, if you move those two variables on the right-hand side to the left-hand side, then the coefficient in front of them becomes negative. So if we go back here, this time pay attention to corn. So it's here, you will notice, say this raised corn, it has a negative coefficient. It's because in this constraint here, this raised corn is on the right-hand side. And if you move to the left-hand side, this 125, you have to add a negative sign there. And also for buy corn, because it's on the right-hand side and the coefficient is 1, if you move it to the left-hand side, then it ended up with a negative 1. And for sell corn, it's on the left-hand side. This one has a coefficient of 1. And for also for the corn constraint, there are corn used to raise cattle, and the coefficient is 25 here, so which is this coefficient here. So that's the explanation of those three constraints, those three inventory constraints. If the word inventory is causing trouble, then maybe you should provide a name yourself for the three constraints, but it's basically describing this relationship of quantities sold plus quantities used is smaller than the summation of the quantities yield and the quantities bought. So that's what those three conditions are about. And I mentioned that there's a different setting of this linear programming problem, and you actually ended up with less constraints and less decision variables. So how can we do this? So we can actually combine the raise and sell of soybeans. So by doing that, we assume that all of the soybean produced or raised will be sold. So we're not keeping some of the quantities for other uses. So for whatever is raised, it's sold. And same thing for the beef. So for whatever beef produced from raising cattle, we sell it because we don't get value from other uses, at least in this example. For example, so if there is a case where, for example, the producer might keep some of the beef for own production, and if we give a cost for that own production, then we might not be able to do what we're doing here to combine the raise and sell. However, in this particular example, we just assume that there's no uses like that. So all of the beef produced are sold. So that's why we can combine this. And we cannot do that for the corn. It's because corn case is a little bit more complicated. The producer is buying corn from the market. The producer is using some of the corn for livestock, for raising cattle, and the producer is also selling corn, growing corn. So we cannot do that for the soybean and beef or cattle. So with that, we actually get rid of two of the inventory conditions. So we only left with one corn inventory conditions. We don't have the cattle and the soybean inventory conditions anymore. And if we change this activity here, so this activity is different from the original setting, then the coefficient that we're using is also different. So this is what looks like in the original setting. You will notice that there's two coefficients there and there's two coefficients there for both soybeans and beef and cattle. However, in the new setting, the coefficient is different. You have to do a little bit more calculation here. So for cattle, I provided how I get this 64, which is 250 minus 186. So this is a 106 and this is 250. Because the unit is consistent, I can just do that. However, for the soybean, you have to do a little bit more calculation. Is we get this new coefficient of 49. So this is 2.5 times the yield, which is 30, and then minus 26. So if you go back to this original setting, you will find this 2.5 here. You will find this minus 26. You actually need to use this 30 there. So in your calculation, this is the soybean. So this 49 is actually the unit profit of raise and sell beans. So this is a revenue, this part, and this is a cost. So they're all per acre. So for the revenue, this is the quantities that you can get from per acre, and this is a unit price. So this is similar to P times Y. So this is a price of the output, and this is a quantity of the output, and that is total revenue, and then minus the total cost. We actually this number is also got from the budget from the table. So if you add different costs together, and you ended up with this total cost. So that's additional calculations you need to do if you're setting your problem differently. So this setting, it is a little bit more cleaner, and but you just have to be aware that if you change your activities, you have to change your coefficient for most of the time. And I another point that I want to mention here is that even if we have two different settings and we use different constraints and different decision variables, the solution from these two settings actually is the same. I can actually show you this in the Excel. So let me show you that. Okay, let me show you the two different settings of this linear programming problem. So in this Excel, there's actually three tabs there. This one, this blanket one, is where I get rid of all the coefficients. So if you want to practice, you should try yourself without looking at the other tabs. Try to put the coefficient here in this area and also in this area. So this is for you to practice. All you need to do is put the coefficient in the right place. There are cells where you need to provide the formula. I have already did it. So if you don't change anything there, then you should be good. And this LP example 1 is one of the settings, is the settings where we didn't combine the cell soybeans and rice soybeans and cell beef and rice cattle. And this LP example 2 is where this is an alternative setting where I did combine them, and you ended up with less constraints. So let's look at this one. And this one, there's already values there, so this is a solved version. Let me actually first get rid of those solutions first. And then this is the setup. You can verify that the coefficient should be the same that I derived from last lecture. And we can do this data and then solver, and here everything has already been set up. This C5, we want to max it, and this C3, 2, and 3 are the decision variables, and there's constraints here. All of the constraints has already been set up so that they're all less or equal to, so you only need one here to represent all of those constraints. And make sure all of the decision variables are non-negative. We're using the simplex method. So if we solve it, then you can kind of already say here that those decision variables have a value. We also have the objective function. So this is the profit, the maximum profit that this producer can get. And good news is here, solver said if the solution, all constraints and optimality conditions are satisfied. And we want to report the answer, and if we want to do some sensitivity analysis, we also want to include the sensitivity report here. So let me produce those two here. And once you do that, you will notice there's an answer report here, and there's a sensitivity report here. So the answer report, you will see this was the value, the final value we got for the objective function, which is the profit. And the original value, we didn't provide anything. You can test by providing different values, see how that change. And we also have here are the decision variables. The original values are all 0 because I didn't provide any, and Excel just assumed there are zeros. Those are the soft decision variables. So this is acres of corn used to raise or grow corn. And we also have some information about the constraints. So we know some constraints are binding, and there are 2 of them are not binding here. So this one is capital borrow. So the producer can borrow up to 25,000 here, but it ended up only borrowed $5,312.5. So this variable here is the slack value, which is the amount that the producer could borrow but didn't end up borrowing. And there's another non-binding constraint is that the producer can raise up to 50 cattle, but to maximize profit, the producer, the producer didn't raise any cattle, and there's this 50 slack value or slack value here. And all of the other constraints are binding, means that here except those 2 that we have just mentioned. For example, if there's 250 acres of land, then the producer used 250 acres of the land. I think I mentioned something wrong here. So this is not the acres of corn raised. This is actually the bushels of the corn sold, and this value is the acres of corn, acres of the land used to raise corn is 250. So that's the information you can get from the answer report. We also generated a sensitivity report, but I will go to this. I will not explain them now, but later on I will go to the details of this sensitivity report. And I want you to pay attention to this objective function value and these decision variables here, because if we have a different setting, let's get rid of those values. So this is a different setting, and I'm just randomly putting some values here. And we can also solve this problem, and again, everything is set up. And if we solve it, you can see that the objective function value is the same if you use the other setting. And for most of the decision variables where it appears both in this setting and in the original setting, those are the same. For example, the corn sell, corn raise, corn buy, and the labors, those decision variables are all the same. So if you use 2 different settings, and if you did set up the problem correctly, then you will end up with the same solution. So again, I want to emphasize here that even if you have 2 different settings, you ended up with the same solution from those 2 different settings. So sometimes it's really, linear programming is really more of art than science. Everyone might have a different way of setting the problem in his or her own mind, and it is possible that one person is setting up the problem differently than the other person, and that is totally normal. But if you do set up your problem the right way or logically, then you should end up with the same solution. So I have shown you guys the answer report, which includes the information about the linear programming problem. We see the decision variable values. We also saw the objective function value, which was the profit being maximized. And here I have to say that even if you are able to solve the problem, sometimes you have to be careful. It's because those solutions are based on some assumptions. And what are the assumptions? So one is that if the parameters of the problem was correctly specified. So for example, in our exam, in the farm management example, we actually use the price for corn and price for soybean, and those two prices actually is prices that the grower assumed that he or she will get when he's selling the product on the market. But however, when the producer is making the decision of how much land to allocate it to corn and how much land to allocate it to soybean, then the producer doesn't know for sure what are the prices. So there could be, the producer could be using a wrong price or prices when making up the decision. So that is one assumption. Another assumption here is that we set up a model, and our solution is actually based on the assumption that the model actually correctly described the decision process. However, sometimes that might not be the case because we assumed that the producer is deciding how much corn and how much soybean to grow in order to maximize the profit. However, it might not be the case that the producer wants to maximize the profit. So again, if the model is not capturing the decision process, then you have to be careful when interpreting your answer or your solutions. So that's not always the case, unfortunately, that we can always model the decision process perfectly, or we have all the parameters of the model specified correctly. But is that the end of the world? No. We can still use some analysis and answer some questions. So here we will do some sensitivity analysis and answer some of the what if questions on the key parameters of the model. For example, if the price of corn changed, then from the results you get from the answer report and also the sensitivity report, then can you answer some of the questions? What if the price changed? Then how will the solution change? Will the producer get more profits, or will the producer allocate the land to grow corn and soybean differently? And that depends. So we have to answer this question based on the information we get, based on the sensitivity report we get from this problem. So before we actually work with the sensitivity report, I want to have a brief introduction of the sensitivity analysis. So it examines how the changes in the parameters. So I can explain what's the parameters of this model. So how the change in the parameters affect the optimal solution. And I also highlighted optimal solution because I want you to be very careful what is the optimal solution, because it might get confused later on when we say if the parameters change, then will the optimal solution change? If you don't fully understand what we mean by optimal solution, then you might get the wrong answer here. So first, what are the parameters? So there are several types of parameters here. One is the objective function coefficients. The other is the right-hand side values. And we also have technical coefficients. In this course, we're not covering the case what will happen to the optimal solution if the technical coefficient change, but we will cover the first two types of parameters. Here is what will happen to the optimal solution if the objective function coefficient change or if the right-hand side value change. So that one those two we will cover in this course. So a little bit more detail, what do I mean by objective function coefficients? We have already actually used these words many times in this course, but maybe some of you are still confused about them. So it is the contribution of each activity or each decision variable to the value of the objective function. So for example, in this setting of the linear programming problem, if we sell soybeans, the coefficient is 2.5 here. And that means if we increase the bushels of the beans sold by 1 unit, then the profit will increase by this amount. And if we raise 1 more acres of corn, then for this activity or this decision variable, that means there will be a $55 cost. So this is contributing negatively to the profit because there's cost of doing that. So that's the objective function value, and what's the right-hand side value. So for most of the time, the right-hand side value is just the endowment of the input that the producer own. For example, the land that the producer own, or the labor that the producer can hire or own. So those are all kind of the input values that the producer own. But sometimes it is not just the input of the producer own. For example, here for this corn inventory constraint, the right-hand side value is actually 0. So it's not any type of the quantities of the input that the producer own. And this constraint is because we moved some variables or decision variables from the right-hand side to the left-hand side. So that's why the right-hand side value is 0. However, we get some negative signs on the left-hand side. So that's the explanation of the objective function value and the right-hand side values. So if you look at this linear programming setting in the Excel spreadsheet, there's actually, I highlighted here, what do I mean by those 3 different types of parameters. So all of those values here, those are the objective function coefficient. And this orange part here, all of those values, we call it the technical coefficient. And this part is the right-hand side values. So RHS means right-hand side. And let me actually make it very clear when we're describing linear programming, what do we mean optimal solution? So optimal solution, we mean the values of the decision variables. So for each decision variable, what is the value that you solved? So it could be you're allocating 250 acres to corn. That is one of your solution. And sometimes if I ask what is the optimal solution, some people might give me this value, and that's not correct because there's another name for this value. This is the objective function value. It's not the optimal solution. So I do want you to be clear that the optimal solution and the objective function value are two different things. And if I ask for optimal solution and you give me the profit, then I will not give you credit because you provided the wrong answer. So be careful what I ask, because this is very important that you differentiate between optimal solution and objective function value. They are different things. If we're clear with what is the optimal solution and what is objective function value, then let's actually continue to do the sensitivity analysis. And this will be mainly based on the information in the sensitivity report. And the way that you generate sensitivity report, I actually showed you a little bit earlier when I was solving this this problem in Excel. It's similar to the way you generate the answer report. So after you click solve, and then there is actually a popped up window asking you whether you want to have those reports. So if you click it there, then you get your sensitivity report. And the sensitivity report actually have two parts. So I'm just copying them here. And this is the part one. Part one is the variable cells. And if you pay enough attention, then you will notice that in the variable cells, it is reporting the objective coefficients there. And there's another part of the sensitivity report, which I call it part two. And this time it is about constraints. And the name there is different. It's called constraints, RH side, which means right-hand side. So that's why I use the RHS previously. So to make sure that when you actually get the report, the sensitivity for a report from Excel, then you actually, it is consistent with the notations that we have been using. So that's actually move on with the sensitivity analysis. As I mentioned, there are three different types of parameters, and we will be looking at objective function coefficient and right-hand side values. We are not looking at the technical coefficients. First is objective function coefficient. Just to be clear, we are looking at this line here, that those are the objective function coefficients there. So for the objective function coefficient, what we can get from the sensitivity report first is the range of optimality. And what does that mean is that it can tell you over what range can a particular objective function coefficient vary without changing the optimal solution. So again, be very careful. The optimal solution means the value of the decision variables. It doesn't mean the objective function value, which sometimes could be profit, other times could be cost. So it is not about that. So the range of optimality can tell you if the objective if the decision variables will change. It cannot tell you whether the objective function value will change or not. So be careful about this range of optimality. It is about optimal solution. So why are we even interested? And I actually mentioned this a little bit. And here, let me make it more explicit here, is that if you know the range of optimality, then if you want to change some of the objective function coefficient, for example, the price of corn or the price of soybean or beef, any of those objective function coefficient, then you don't need to resolve the problem when you change those coefficient objective function coefficients. And of course, this is the new objective function coefficient need to be within the range of optimality. So if the new objective function coefficient that you are providing is within that range, then you actually don't need to change. You actually don't need to solve the linear problem again. You already know what the solutions are. So that's one way. And another reason that you're interested is because it can provide you some information about how sensitive the solution of your model is to the parameters of those of the linear programming model that you have just set up. So let's actually take a look at the sensitivity report here, and let's focus on the cell corn coefficient. I have been using this as an example. So from your sensitivity report, the first line or the first row here is cell corn. So you have to be careful about which objective function coefficient you're looking at. So here we're looking at cell corn, and this is the solution, the optimal solution. This 31250 bushels of corn should be sold. And we are really interested in the objective function coefficient. Before we mentioned that the price to sell corn is 1.3. This is what you can get from the budget, the corn budget, the table. And in the sensitivity report, the most important information are actually here. So those two values, one is allowable increase, the other is allowable decrease. What does that mean is that if you're increasing this objective function coefficient, and as long as the increase is less than this amount, then you still get this optimal solution. You don't need to solve your linear programming problem again. So just give you an example. For example, if it's 1.4, the new objective function coefficient, suppose that at the time of the decision, you think you predict the corn price is 1.3. However, it could be 1.4. And if that's the case, then what will happen to the decision of the producer? So since this 1.4 minus 1.3 is 0.1, and this 0.1 is smaller than this 0.184, so that actually means that your solution will not change. So be careful of the word I'm using. The solution will not change means this value here will not change. It doesn't mean the final profit will not change. So the profit is your objective function value. So here it is only tell you optimal solution doesn't change. It doesn't tell you that profit doesn't change. So I hope I made it very clear about that. So after you got your sensitivity report, and you can ask the question, what happens to the optimal solution? Again, optimal solution is the values of the decision variables. So if the corn price is 1.5, 1.4, or if it's actually lower than the producer expected. So what if it's 1 or 0.9? We already studied the case when it's 1.4, but what could happen to 1.5 or 1 or 0.9. So here in this blue box, I actually provided some description of the problem we have been seeing is that if the farm manager or the farmer is uncertain about the selling price of corn, it could go up or down for various reasons. But if the corn price change, what will be the impact? This is actually not profit. Well, what will be the impact on the optimal solution? And depending on your answer to the optimal solution, then you can also tell what is the impact on the profit. So here, again, first is that optimal solution, which is a value here. The optimal solution does not change if the price is between those two values. So those two values actually described the range of optimality. And how did we actually get those two weird numbers? So this is from your sensitivity report. So based on your coefficient, the allowable increase and the allowable decrease, you will be able to get those two numbers. And I actually have it here. So this number is actually 1.3 minus this 0.35868. So this is the allowable decrease. So decrease, we use the minus sign here. So for the objective function coefficient you provided, and minus the allowable decrease. And for this value is plus, because this is increase. So 1.3 plus the allowable increase. So if it is within this range, then the optimal solution will not change. However, for example, if the increase is 0.3, which is larger than this value, and you ended up with a new coefficient of 1.6, then the solution will change. We don't know what the solutions are. You have to solve the linear problem again. However, if it's within this range, then you don't need to solve your problem. You already know what the optimal solutions are. So based on this range of optimality, so this is the range here, I put it here, then we can actually answer the question we asked before. What if those are the actual corn prices? Then what will happen to the optimal solution? So remember, it's the optimal solution here. So we will check this 1.5. Is this 1.5 within this range? No, it's because the maximum price allowed here is 1.48. So it means the solution will change. And if it's 1.4 and 1, they are both within this range. So your optimal solution does not change. And what if it's 0.9? So if the price is 0.9, it's out of this range. It's smaller than the lowest price that's allowed, and your solution will change. So then, based on the information, you can actually answer the question of, or not able or able to answer the question of what happens to the profit, which is the objective function value. So this is not the optimal solution. This is the objective function value. Then you can also answer what will happen to the profit. So those two values are within the range. Then we know the optimal solution doesn't change. So the corn that's gonna be sold is still those amounts. And because this 1.4 increased by $0.1 compared to this original price. So this is the price increased, and this is the optimal solution. And if you take the product of those two, that is actually the increase in your profit. So if you calculate this number, then it will be this amount, $3,125. So that is the increase in your profit or your objective function value. You can also answer this question, what if the corn price decreased to $1 because it's still within the range, then the optimal solution doesn't change. And the price decreased by 0.3 per bushel, and the optimal solution doesn't change. So this, if you take the product of those two, and I think it's maybe, let me do it here, 9.3. This is the amount of the reduction in the profit if the corn price is $1. And what if the price is either 1.5 or 0.9? Can we tell from the sensitivity report what will happen to the profit? No. Why? It's because the optimal solution under those two prices will change. So we don't know what the new solutions are, and you have to solve the problem again to be able to tell that information.